What I'd like to do this afternoon is to introduce Ozalp Babaoglu, who is a full professor at Bologna, Computer Science and Engineering, and he's going to be talking to us about some stuff around his ideas around sustainable computing with data science. Thank you.
Thank you, John. I'd like to thank also Eric Schmidt, who organized our social visit to Google today with my family. First time I'm here at Google, and I'm very, very delighted to be here. Thank John for organizing the talk. So what I want to do is present you some ideas that we have, and this is joint work with my postdoc Alina Sirbu. Questions regarding how to make high-performance computing sustainable, and the main point I want to get through to you is the use of data science and data-driven techniques. So the HPC, high-performance computing, has this holy grail of exascale computing, which is 10 to the 18th operations per second. This is picked as a goal because it's commonly believed that at that rate of that speed of computing, we could have machines come close to the power of the human brain. So this is seen as a holy grail. Now the initial timeline for reaching this goal was set to 2018, but recently it's been pushed forward due to all of the technical problems that you can imagine. So reaching this goal in HPC obviously requires significant advances initially, first in hardware technologies like raw processing power, also parallelization techniques at the hardware level and at the software level, because to get to these speeds, obviously we need massive parallelization, both in the number of computers and also in the software threads. So we imagine millions of computing elements with billions of threads to achieve the goal. And the other issues have to do with power efficiency, power dissipation, and just the sheer management and control of this entire infrastructure because of the scale. And what I'm trying to convey today is that these problems, to address them, we really need to have a holistic approach. That is, we cannot concentrate on subsystems in isolation, but need to look at the big picture in its whole. So what I want to do is relate this problem perhaps to you and Google, in that I believe that many of the issues having to do with HPC reaching exascale performance can be related also to large data centers, which I think makes the problem quite relevant to an audience such as yourself, because a large data centers essentially replicate many of the problems that exascale HPC computing does, especially with regard to management and control. So this is a data center in the right lower corner. But what I want to do with this picture is just put that in context to you. And this is what I mean by a holistic approach. That is, we don't want to look at the data center in isolation, but because it's part of a huge ecosystem that includes many other elements. And I indicated some of them in the block diagram, having to do with all the way from the power generation station that provides the electrical power to get it up to the data center, the backup UPS facilities, the seismic security having to do with earthquakes, and the entire non-negligible, on the contrary, quite a considerable part of a data center has to do with the cooling. So we need to dissipate all of the heat that's generated. So the data center itself is only a tiny piece of this big picture. So what I'm advocating is that the sustainability question really needs to be addressed looking at the big picture and not concentrating just on the computing element. So how do we do management today, at least in the context of a data center? Well, these are some of the tools that have been developed over the years. I've listed some of them, and many of them have been developed right here at Google by people like John. But what I can say is that most of these tools help us in automating some of the low-level infrastructure provisioning and resource allocation. But even at their best, the human element, the operator, remains an integral part of the management structure. That is, we cannot completely take the human element out of the loop. And if we want to scale these data centers to millions of computing elements, then we're going, if you scale the number of operators currently employed in a typical data center by several orders of magnitude, we end up with armies of operators. And that I claim is not sustainable. So we need to address that. And operators in a data center are quite often detrimental rather than useful. So this is a statistic taken from a study, the most recent being 2013. So this is ranking the root sources of outages in data centers. At the top we have the UPS power system failure accounts to, and these are for 2 fiscal years, 2013 and 2010. In the 2013 case, the power failure accounts to about 1/4 of the outages. And if you notice, the second most common source of a outage is the human element. So this is the accidental human error. So these are the so-called oops errors that operators commit while doing routine maintenance or update operations. So this is absolutely not something that we cannot ignore. So and if we increase the number of operators in the data center, this percentage can only get bigger. So the role of operators, this is a quote, I'll just read it to you. One of the biggest opportunities for entrepreneurs in the enterprise is cutting out the human IT staff and going full automation, potentially with technologies like deep learning. It's ridiculous to have humans manage the level of complexity that we have inside the data center. And the quote is due to Vinod Khosla, who I'm sure many of you know. He's a noted venture capitalist and technologist, one of the founders of Sun Microsystems. And this was something he said at a meeting in 2014. So this is this vision of the human operator in the data center as being detrimental is something that's shared. It's not just my paranoia, but it's also shared by other people. So what I want to propose is a shift from human-driven to data-driven. And so certainly progress in hardware technologies is going to be fundamental and necessary for scaling up both the data center and HPC. But we also need to scale up software technologies, in particular in the form of in the management arena, so as to get the role of, redefine the role of human operators in the data center from shifting from nuts and bolts operations to setting up high-level goals and objectives. So the human element in the data center should only be setting high-level goals and let the software technologies that we develop do the routine maintenance operations. And at that point, we'll have large computing centers and HP systems. Their operations should be based on predictive computational models obtained through data science, and that's what I'm going to be concentrating on today. So what I want to do in this talk is give you one data point towards this objective of achieving shifting from human to data-driven techniques. And I will do that by focusing on the aspect of sustainability that has to do with long-lasting computations. That is, computations to be sustainable should not be interrupted by events such as errors or failures. So the question that the hypothesis that I'm trying to test is, can we use data that is contained in routine typical data logs that are collected in typical data centers? Can we use that information to build predictive models to be useful towards the sustainability goal? And the sustainability goal for this talk is going to be failure detection, failure prediction. But in general, we can use the same techniques also for other aspects of sustainability having to do with power, energy consumption, and cooling, and other aspects. And I've indicated 2 other work that we have done exactly in this arena, having to do with building predictive models for power consumption in a HPC setting, not in a data center setting, but an HPC setting. One collected from an IBM Blue Gene Q installation that we have access to in Bologna, and the second one being a research machine, again built in Bologna, called the Aurora. That is a hybrid HPC system that puts together CPUs, GPUs, and mix to achieve very high performance. So what I propose is a form of autonomic computing that I call data-driven autonomics. And it's based on the idea that, just as I showed you in the picture, the data center is not an object in isolation, but it's embedded in a data-rich environment. The data-rich environment can be as large as you want. It can include the cooling, power, structure, but it can also include the physical environment, like the seismic activity, automobile traffic in the arena. It can even include geopolitical considerations that take place in that arena, and earthquakes, why not? So it can be as large as you want by bringing in more data sources into the consideration. So the question is then, can these data be exploited to devise a new class of autonomics that I call data-driven autonomics? So what are the main salient points of such an autonomic computing system? Well, first of all, as I said, it should be holistic, meaning that it should consider the data center not in isolation, but in the bigger picture. And the bigger picture, as I said, can be as big as you want, depending on what you bring in. It should be data-driven, that it should use modern data science techniques to exploit massive amounts of data that are collected from multiple sources. It should be predictive, as opposed to descriptive. It should be predictive in that it should anticipate unwanted future states so that we can avoid them. It should be rule-based, interpret the predictions in the context of larger high-level policies. It should be proactive rather than reactive, that is, it should anticipate unwanted, undesired states and avoid them in the first place rather than reacting to them after they have occurred. And the ultimate goal, as I said, is to limit the role of the human operator. So in that sense, these goals are very similar to what we have for things like self-driving cars. I can list essentially the same properties that we list for a self-driving vehicle: predictive, rule-based, proactive. So what I want to do is apply these same ideas in the case of sustainable high-performance computing. So what we did was test this idea on one particular data that we have access to, which happens to be the Google dataset that John has collected and made publicly available for researchers. So this is just a very short summary of that data. Maybe I'm boring you, that you probably know some of this. But anyway, it's a data set collected from about 12,000 machines over a 1-month period. It's roughly 200 gigabytes of raw data. And the data contains elements that have to do with task events regarding the state and the number of tasks on each machine. It includes the task usage logs having to do with the resource consumption of each task, and then machine events that indicate when machines are added or removed from the cluster, either due to failures or due to maintenance events. So what we did was use this data and apply machine learning techniques to build a predictive model. And the first thing we did was to select the features. So the first thing we did, we extracted 12 what I call base features over 5-minute windows. And the 12 basic features are the number of running, started, finished, failed, killed, evicted, lost tasks on each machine. So these are the different states that a task can be on for each machine. And we count the number of tasks in each one of those states. We also add to the feature set the machine load in the form of average CPU load, the memory load, the cycles per instruction, the CPI load, the memory accesses per instruction, and the disk time. So these are all available in the raw data. So we extract these at 5-minute intervals per machine and then aggregate them. And then we also compute aggregate features. These are averages and standard deviations and coefficient of variations over longer intervals, not 5 minutes, but longer, longer being 1, 12, 24, 48, 72, and 96 hours. And then finally, we select 7 features and compute pairwise correlations between them. So this adds 21 more features. If you do the 7 choose 2, that's 21. So this adds 21 more features. So in the end, we end up with 416 total features, accounting to a very modest amount of data, 104 megabytes. So it's, the size of the data is not an issue at all. So this is this is a picture of a time series of some of these features for one particular node in that 12,000 cluster that we have access to. So this is time running horizontally, and the features that I'm illustrating with the various colors happen to be the CPU load at the 5-minute interval, the CPU load but now at the 12-hour average, the CPU load at the 12-hour coefficient of variation, and then the pairwise CPU load running job 12-hour correlation. The actual values are not terribly important. I'm just showing you what a typical time series data looks like. But what I'm also showing is that big gap in the middle, that white space. For this particular node that I'm examining, that node happens to have been removed at around 250 hours and then added back into the cluster at 350 hours roughly. So in that interval, the node was absent either because it failed or it was undergoing some sort of update maintenance operation. So then we analyzed these features using one of your tools, BigQuery, that we had access to. So we did pre-processing of the features using BigQuery. These are some features of BigQuery that I'll skip because I'm sure you know about them. I'll only highlight the fact that the whole pre-processing operation on BigQuery costs less than $2,000 using real Google pricing. So this is something quite, it's not an unreasonable amount of expense. Excuse me? Highway robbery. And this is a more detailed breakdown of the BigQuery pre-processing in terms of the first column are the aggregation interval ranging from 1 hour up to 96 hours. And then the second column is the resulting data size ranging from 1/10 of a terabyte all the way up to 12.5 terabytes. And then the last two columns are the times, actual times required to compute the average standard deviation coefficient of variation, which is the third column, and the last column, which is the most time-consuming computation, having to do with the pairwise coefficient of variation computation. Now, this is interesting because it's, at least as far as I know, it's one of the first quantitative results of BigQuery performance on real data. In itself, it's not really relevant to what I'm doing, but it's just giving us a feeling for the performance of BigQuery, which we were very, very happy to use. I mean, it made our work feasible. Otherwise, we wouldn't, if we were to do this on local infrastructure, we would not have been able to do it. So now continuing on to what I want to get at, which is a predictive model for failures, the first thing we need to recognize is the fact that the Google trace does not have failure events. There is nothing in the Google trace that's labeled a failure. There are machine adds and machine removes, node adds and node removes. So failures can only be inferred indirectly and approximately, because obviously we don't have certainty. And here we consulted John on how we might do this. So we came up with the following heuristic, which was, if a machine remove event is not succeeded within the next 2 hours by the same node being added, we deem it to be a failure. So the reasoning being, if it were a routine maintenance or an update event, the node would be removed from the cluster, but then would reappear in the cluster after some reasonable amount of time. And we chose 2 hours to be this reasonable amount of time. Now you can question that, obviously, and I don't have any specific reason why that should be but again, as I said, this was not something that we made up completely on our own. We consulted our colleagues here. So take that as it may. So 2 hours, less than 2 hours, is considered a routine maintenance event. If it's more than 2 hours, we assume that the machine failed and then was somehow repaired and put back into the cluster. So this is going to be my definition of what a failure is. So at that point, we classify each data point as either a fail, which I call the positive class, and the safe, which is the negative class. So in terms of the classifier language, the positive class corresponds to failures, and the negative class corresponds to safe or non-failure. So a positive event is considered to be time to failure is less than 24 hours. So we chose a window of a day. So if the machine happens to be labeled in the failure state within a day, we call that data point to be in the fail class. And if it's greater than 24 hours, it's considered to be in the safe class. Is that clear? Okay. And the resulting number of data points were given in the previous slide. So we end up with some 100. Well, I should go back to that because that's important. Sorry. So doing this, we end up with 108,000 positive events, meaning failure events, and we end up with 500,000 safe events, but that's only after a 0.5% random sampling. Because if we don't do the random sampling, the number of safe states is overwhelming because most of the time failures don't occur. So you have machines that typically don't fail. So if we were to keep all of the safe states, then the two classes would be extremely unbalanced, and most of the machine learning techniques that we use do not perform well when you do a classifier with such different ratios of the two states. So we do a 0.5% subsampling, meaning that we throw away 95% of the safe states and we pick a random 0.5% sample. Sorry, not 95, 99.5% are thrown out, and the 0.5% are randomly sampled and kept as the safe state. So the classifier itself is a random forest classifier. This is a well-known machine learning technique based on decision trees. I'll go very fast here since I'm I assume most of you are familiar with these techniques. So we generate a large set of random forest classifiers and we train them, and then we compute their precision of each one based on a data set which is different from the data set we use to do the evaluation. So the data set, the test data set, is divided into two halves. The individual data set, which is used to compute the precision, and the ensemble data set, which is used to build the ensemble classifier through precision-weighted voting, which I will explain in the next slide. So we end up with 420 individual random forest classifiers, and we build them as follows. We vary the number of decision trees between 2 and 15, so there are 14 of them. We vary the ratio between safe and fail data events between 1/4 and 4. So this determines the number of subsampling percentage that I talked about just a few minutes ago. So we either throw out more or less of the safe data between those intervals, and then we repeat the whole thing 5 times. So when you do all of the math, you end up with 420. So we end up with 420 RF classifiers, and we train each of them on 10 consecutive days, and then we test on the next disjoint day. So remember that the Google data trace has 29 days of data. So if you look at the picture in the bottom, so for benchmark 1, we skip the first 2 days because we don't want, we want the aggregate to start working, because if we do aggregation over the previous days, if we start from day 0, we don't have anything to aggregate. So we start in day 3, so the blue days are the training data, then we skip a day, and then on the 11th day, that's our test data. And we do this by shifting this picture 1 day to the right, and we end up with the 15 benchmarks that cover the entire 29 days of the trace. So these are we have 15 benchmarks to do the testing. So going back to the ensemble classifier, we had 420 classifiers, and we merge all of them into an ensemble classifier. So we have ensembles of ensembles, because remember, random forest itself is an ensemble, because it's based on individual trees which are built into a forest. So we have a forest of forests, 420 of them, and we combine them by doing a weighted sum based on the precision. So we take, if you take the ith random forest classifier and take its output, which is shown as sigma ij, which is a binary value indicating it's either in the fail or the safe state. So for the data point j, and we compute the precision of the ith classifier, that's indicated as pi, and then the weighted sum of the output with the precision summed over all of the 420 classifiers is labeled Sj. So the Sj value is no longer a binary value, it's a real value, because we normalize it we scale it by the appropriate value, so we get a number between 0 and 1, so that we can interpret it as a probability. So the weighted value can be seen as a likelihood of failure. So it's not a binary classifier, it's not 1, 0, but it's a real number. So closer to 1 is more likely to fail, closer to 0 is less likely to fail. So this is the ensemble classifier. So now the prediction, yeah. So the weighting is done only on the outputs of the individual classifiers as I have defined the states. So you're right that some of the outputs may be missing because we simply did not consider those are excluded. I don't know what else to say. They're not included in the ensemble, and obviously this will have a consequence on yeah. So we'll see the evaluation results, and you can judge whether it's good enough or not. So now the prediction of failures now becomes a classification problem. And by applying the model, you just evaluate the Ensemble classifier for a particular data point. And then you interpret the result as the likelihood of failure. Okay? And then we can now convert this back to a binary classifier by setting a threshold. So you can say if the likelihood is more than 80%, I'll consider the output to be a failure. So the training was done on a absolutely ordinary routine desktop computer, an iMac, very moderate performance iMac. And this was just to show you that the training is a very lightweight operation. It took between 7 and 9 hours on a single desktop computer. So we don't need any sort of high power computing to do the training. So these are the results. So the results for a binary classifier is typical to display these ROC curves that I'm sure you're familiar with. So I'm plotting the true positive rate in the vertical axis as a function of the false positive rate. So the true positive rate is the number of positives that are actually classified as positive, and the horizontal scale is the number of negatives that are identified as positive. So these are the false alarms, if you will. So ideally, we want to be in the upper left-hand corner because you want the true positive to be 1 and you want the false positive to be 0. But obviously, life is more complicated, so we get these curves. So the solid line is the Ensemble classifier. And I'm showing you this for 2 different benchmarks, the left one being the best case. Remember, we had 15 benchmarks. So this is the 14th in that among those 15. And the worst case happens to be the benchmark number 4 on the right. So let's look at the best case. So the solid line is the Ensemble classifier, and the individual colored dots are the individual pieces of the ensemble. And the colors correspond to different ratios among the false, fail, and safe events. Remember, I defined this. I told you we were doing the subsampling, and we were varying it between a quarter and 4. So these are the different colors. The dark blue is the 0.25, and the whatever that color that is, yellow is the case when the ratio is 4 to 1, as opposed to a quarter to 1. But anyway, the takeaway is that the ensemble typically performs better than the individual classifiers, which is good. So it means that by putting individual classifiers together under a single ensemble, we do better than any one of them individually, because rarely any of the dots are above the solid line. And the other encouraging point is that the curve, even though it's not ideal, it's close to our desire, which is being in the upper right-hand corner. It's typical to pick the false positive rate to be 5%, and if you do that, so that's this vertical, the yellow vertical line, this point here, you end up with the true positive rate in the best case to be 88%, and in the worst case to be 27%. Now the other evaluation of a predictive model is the precision recall curves. So these are plotting the precision, meaning that what is the probability that an event marked as a failure is really a failure as a function of the recall, which is the true positive rate. And in this case, we would like the curve to be essentially a horizontal line and then dropping off to 0. And here we do less well. The best case looks pretty reasonable, but the worst case is significantly below the ideal. And in this case, we also see that some of the individual members of the ensemble do better than the ensemble, at least for the worst case. But again, if we pick the 5% false positive rate as a threshold, we end up with precision recall values that range from 72 and 50. So just summing up, If we limit the false alarms to 5%, in the best case, we can identify almost 90% of the failures. And 72% of those failures that are identified as failures are indeed failures. And in the worst case, we are able to identify only 30% of the events as failures. And in that case, about half of them are actually failures. So this sums up the evaluation. You can also summarize them as these areas under the ROC and PR curves, but I'll skip that. Next you may ask, prediction is not perfect. Sometimes we misclassify events. So how bad are the misclassifications? So how wrong are they? So the classes for the fail class, the positive class, remember we identify the fail class as being a failure occurring within the next 24 hours. So an event would be included in the fail class if the failure occurred even 1 minute in the future or 23 hours into the future, because both of those are within the next day. But intuitively, obviously, those two scenarios would be very different. If you have a failure coming up in a minute as opposed to 23 hours, perhaps you would do different things. So classifying both of them as failure should not be technically is correct, but qualitatively they should be seen differently. And likewise, in the negative case, the failure is outside of the 24-hour window if it occurs at 24 hours and 1 minute as opposed to 2 weeks. Again, technically both of those are safe states, but again, intuitively you perhaps might do different things in those two cases. How the classifier performed in practice, I'm showing you this for the benchmark 4. So these are box plots for the time hours to next remove event. Hours to next remove event as a function of I'm showing you the true positive and the false negative. So on the left picture, these are the case when the event is marked as a failure, either because it's a true positive, a failure, or it's incorrectly marked as a failure even though it was a safe event. So the thing to note is that the case when the true positive median, the red line in the bow of the bow tie is the median value. In the case of TP, the true positive is lower than the false negative. So what that means is that in the case of a failure that's actually marked as a failure, we mark it as a failure closer to the failure than if it were a misclassification. Now, why is that good? Well, if the event is misclassified as a failure later, that means that you have more time to, because remember, we're doing this at 5-minute intervals. So we have more opportunity to mark it correctly in the future. So we mark it as a failure if it's further away, because that gives us more time to classify it correctly in the future. If it were misclassified and it was imminent, then the classification would be wrong, and that's all there is to it. But so the misclassification, if it's further away, is deemed to be better because, as I said, it gives us more chance to classify it correctly in the future. And then I'll skip the right curve. So putting all this together, how would you use such a predictive model? Well, you would perhaps use it to do some intelligent form of scheduling. So one idea would be to define this notion of a quarantine. So a node that is classified as a failure in 2 consecutive evaluations, we put it into a quarantine state. And if a machine is in the quarantine state, the scheduler does not dispatch any tasks to it. Tasks that would be dispatched to that node are diverted to other nodes. when you do that, two things could happen. You could redirect a task to a node that was marked as that is in the quarantine state, but the failure was sufficiently ahead such that the task would have finished before the failure. So that's bad. It means that you redirected a task without any without reason. You could have avoided that. Or you could have redirected the task and it would have been interrupted. That is, while it was running, you would have had the failure, and you avoided that interruption, so that's the good case. So we have these two outputs. The redirected without reason is bad, and the recovered is what I call the second case, meaning that you avoided dispatching the job to a node which was in the quarantine, and that's the good case. And you obviously want to your objective is to minimize the redirected and maximize the recovered. Obviously, if you redirect everybody, nobody will be interrupted and the recovered will be as high as well, but you would have, that would be like taking that node out of the picture altogether. So that's obviously something you want to avoid. So you want to keep the node in the cluster, but you just want to avoid sending tasks to it that you know will be interrupted. So we evaluated this idea, but to do the evaluation, we need a base case. And the base case was defined to be the result of these two events, recovered and redirected, if we had a perfect predictor. Meaning that suppose we could predict failures perfectly within the next 24 hours, that is 24 hours in advance. So if a failure can be predicted perfectly a day in advance, that case is what I'm taking as my baseline, the best case. So doing that, we end up with pictures like this. So here I'm plotting tasks that are recovered in the top left picture. So the solid line at the top is the base case, and the three dotted curves correspond to our real predictive model for varying amounts of false positive rates. So we considered false positive rates of 5%, 1%, and 2%. So if you, for example, if you take, as a function of the quarantine window size, if you take the 250 as a concrete value, because we take that because here we match the baseline in the case of false positive rate of 2%, and the resulting task recovered for 250 happens to be about a half of the baseline. So if you limit the false positive rates to 2% and your number of redirected tasks are as good as in the baseline, then you can recover about half of the tasks that you would if you had a perfect 24-hour predictor. And so, and the right-hand curves are the same two situations, but in terms of CPU hours that are redirected and saved as opposed to number of tasks. Okay. Now there's some technical details here which I've skipped, but they're included in a paper that if you want to look at them, because the Google Trace also has different classes of the tasks depending on their length. So we're only doing this for the class 0, the short-running tasks. Now we're not looking at the long-running production tasks. So I skipped a lot of detail here. So again, now going back to the big picture, how could you put these ideas and build an autonomic controller? So first of all, an autonomic data-driven controller, I claim should have these requirements. It should be closed in the sense that it should run on the same infrastructure that you're trying to control and not require an infrastructure of its own. That is, to control a data center, you don't want to build another data center next to it do the management. That obviously something that you want to avoid. It should be non-intrusive. That is, the load that it generates should be quite modest and not be an overwhelming strain on the data center. And it should run in real time. That is, it should run on data that's being streamed to it as data is generated, and do the prediction for the future. So we did a feasibility study of this idea. So the monitoring system to do the live streaming of the data directly to BigQuery, at least for the amount of data that we analyze, would require only 25 cents per day. And every 5 minutes recompute the features in parallel would require about 0.2 of a second per feature. And to store the previously computed features for the last 12 days would require about 122 gigabytes of storage. And adding all of this up at real pricing, Google pricing, this would end up being about $60 a day, which is nothing. Yeah.
Yeah, so one question I have is, are you taking into consideration the failure of the autonomic controller itself?
Yeah, that's a good question. Obviously, the autonomic controller itself is running on the infrastructure which you're trying to control and predict, and it's obviously subject to the same type of events. It could also fail, in which case you would have to replicate some of the pieces so as to in this computation, I'm not considering that. So yes, you would, if that's a concern, you would obviously render the autonomic controller fault tolerant, and by using the appropriate techniques of replication or yeah. But that's not included here. So building them, once you have the features, you would build the model from the last 12 days of data, and then train it on the data itself, and again based on real numbers from something like the compute engine that will require about 3 minutes per random forest. Again, quite a reasonable amount of time. And then once you have the model, applying it every 5 minutes after computing the features, applying the model is really negligible. It's extremely lightweight and doesn't really require any heavy computation. So I didn't even put a number for that. So the conclusion being that the feasibility, at least for the dimensions, the sizes that we considered, are quite practical. It's not something that's infeasible. You could easily run it on a typical infrastructure at costs that are really very contained. So what the takeaway points that I try to communicate to you are the following. Autonomic controllers need to be data driven, and we can use modern data science techniques to help us build them, to overcome some of the challenges of scale and complexity. I outlined such a data-driven autonomic controller to you, not in infinite detail, but a very high-level description. And the other main point that I want to get across is that data that are contained in typical logs that are collected in HPC or data centers are rich enough to build useful predictive models. Now, the situation can only get better if you were to do this in-house. Remember, we're doing this from an outside of, we're not Google. We use the public Google Trace to do this. If I were Google itself, I could collect more data, right?
We do.
You do. You do. Unfortunately, most of that is not publicly available. So by using proprietary in-house more detailed log data, the situation can only get better, is my point. And you would obviously do this. And the other point that I try to get across repeatedly is this holistic approach. In this particular work, it's not particularly, I did not have any empirical evidence for that, but in the energy consumption predictive modeling work that I alluded to, this holistic approach is really fundamental. That is, you don't want to look at subsystems as in isolation, but you really want to look at the big picture, even by doing cross-correlation of subsystems that you did not even consider would be related. By doing the wildest crossing features that you thought were completely irrelevant and unrelated, by crossing them together, you get features that are extremely interesting and important. And the data-driven autonomous controller can be made practical. So this is 3 papers that are related to what I talked about, and if you want to look at some of the technical detail, you can do that by looking at the papers. Thank you. Oh, sorry.
Can you say again how many remove or true fail events there were in your data set?
Well,
100 some?
Well, I can tell you the number of remove events. If you by true you mean true failures, as I said, I don't know that. As I defined them, I had the numbers some slides back. 158,000, I think. Right.
Of the features you actually had in this data set, is there one where if you took it out considerably worsened things?
That's a good question. We did the principal component analysis of the data, and the conclusion was that no, we couldn't, we were not able to really rank the features in any reasonable manner so that we could keep a subset and throw out the others. So even though it might sound somewhat counterintuitive, all of the 420 some features were important, at least according to the technique that we were using. So we could not throw out any of them.
Well, I think that's. Thank you very much.
Thank you very much.